Good day. My name is Cesar Augusto Ramos Sanchez, lead study engineer at PTI S.A., and it's for me a pleasure to host today's presentations entitled HBR Flash Case Study Using ArcFault Solution for Utility in South America. The agenda of this presentation is composed by, first, a brief description of the study case, the utility substations in South America. Secondly, background in the occupational safety and Colombia regulations related arc flash analysis. Next, a quick look into the challenges of AB arc flash study. For a review of the nowadays industry accepted methods, the details of the analysis performed and the tools used, and finally, the analysis results, recommendations, and conclusions. Background. One of the three largest utilities in South America with hydro, renewables, generations, and T&D, with a presence in Colombia, Panamá, Costa Rica, and Honduras, servicing more than 1 million users, prosumers. During the recent years, the utility has been improving its electrical network and procedures, looking for compliance with Colombian and international regulations in the ever-changing grid challenges. The scope of this flash study were analyzed 5 substations in Valle del Cauca, Colombia. Substation 1 with a voltage of 34.5 kilovolts, substation 2 from 115 to 30.2 kilovolt, substation 3 34.5 kilovolt, substation 4 115 to 13.2 kilovolt, and substation 5 30.5 and 13.8 kilovolt. High voltage flash studies may involve large regions covered by both transmission and distribution systems. For the scope of this project, we're looking at the substations mainly. The study case of the performed analysis were mainly substations in double bar, double HPCV configuration with short circuit levels of 15 kiloampere for 115 kilovolt, 25 kiloampere for 34.5 kilovolt respectively. The substations types are subtransmission and medium voltage distribution respectively. As we may see in the schematic diagram, 150 30.5 kilovolt voltage levels are used for the transmission and distribution circuits, and 13.2 kilovolt is used for auxiliary services in the installation. It's worth to mention that the equipment gaps and dimensions were considered within the range of the available methods. The main regulatory guideline in Colombia for arc flash is the Technical Regulation for Electrical Installations, RETIE. This includes low voltage and HBR flash. Because of that, we decided to use ArcFault module in order to run the simulations and analysis. RETIE sets mandatory compliance with safety procedures described in NFPA 70E or IEEE 60634 in the US OSHA 1910.269 can be considered an equivalent of this South American Safety Regulation Organization. Among the mandatory requisites of the Colombian regulations are: first, performing a risk analysis and a flash study in the range of 50 volts to 550 kilovolts. Of course, the high voltage or flash or ArcFault is done for voltage of above 15 kilovolt. Below this voltage, the IEEE 1584-2018 method is used. Arc flash and shock hazard warning labels with minimum requirements complying with ANSI Z535-2011. Third, executing the area or field demarcation with the specified boundaries according to this study. Four, offering the appropriate training for energized work and PPE to personnel. Challenges of high voltage RF flash. One of the main challenges in our flash analysis is that every study requires three different software to run the analysis. First one for short circuits, second one for checking protected device coordination and selectivity, and last one for the HBR flash analysis. Wrapping the two next points, it's important to mention that there is a need for more refined and up-to-date modules to ensure proper alignment safety. Also, there is a lack of Colombian standards and tests available for performing HBR flash analysis. That is the reason why we recommended ArcFault in this type of installations, according to an NFPA 70E. Roughly, conventional analysis is not realistic according to specialized literature, and that is an opportunity to employ ArcFault module. Let's review the following example steps that could give us an insight to assess the amount of man-hours and effort required to do an R-flash analysis prior to an ArcFault module, as we pointed previously. Step 1, use program A to run short circuit about 45 hours. Step 2, use program A short circuit results into program B to obtain fault clearing time over 85 hours. Step 3, manually take program A and B results into program C to determine the ARC flash results, often one location at a time, over 130 hours. That gives us a total analysis time of plus 260 hours. Therefore, our full solution proven to reduce significantly the cost of study with this fully integrated interface using only one database to perform all calculations. Also, modeling and data entry cost reduced greatly as the software gives us to fully access to fully validated and verified software protected device libraries and allowing the use of global typical parameters based on NESC. PD sequence of operation, intuitive and detailed simulations for negative and zero sequence functions improve the determination of the fault clearance times. And finally, the ArcFlash result analyzers allow quick determination of the worst case incident energy and a detailed outlook of the additional ArcFlash related parameters. Two noteworthy models have been developed for HBR flash applications. For further details on these developments, please see Method 1 for Terziha and Conklin for IC and German R flash method, and Method 2, EPRI report 10-186-93, 2009 from ANSI IEEE. The method selected for performing the study for our client was Method 1 of Terziha Conklin, as we see more in detail up next. Unlike the IEEE 1584-2018, ArcFault Method 1 requires the calculation of the actual arc voltage and resistance. The equations shown here show the calculation of the arc voltage, which is highly dependent on the gap length. The equations presented here are more in line with IC-based short circuit calculations. Since in this project, the short circuit standard used was IC, this method was selected. How the analysis is performed, assumptions. Even though we had some actual gas insulated switch gears, it's assumed that the arc will happen like in any other standard metal-clad non-gas insulated switch gear. The arc flash boundary may sometimes be determined based on other threshold energy values depending on the minimum PPE level requirements of the facility. Yet for this location, 1.2 calories per centimeter squared were used. Sometimes, in close location, the arc flash boundary may be approaching or encroaching the physical dimensions of the room. It's worth to mention that the working distances and gaps selected were based on typical NESC C2 2017 data. Our high voltage or flash input data. We have both bay and interior substations. The types of fault analyzed were considered according to worker with tools in positions with working distances that are unnormative for HV structures. Nevertheless, the gaps were adjusted for the interior substations and Gs and metal clad, considering the worst case scenario for incident energy calculation. The slide shows further examples of working conditions or tasks performed around high voltage substations. The image of the right hand introduces the concept of switching operations with additional distance or hot sticks. The working distance be used when using tools is a factor to be considered under NESC for selecting the working distance. Now the tasks on the right-hand side are outside the scope of the substations analysis, but I decide to include them for illustration purposes of other tasks performed around transmission and distribution equipment, which may need to be considered when running an HPR flash analysis. Following with the assumptions, fault impedance is assumed to be zero. Incident energy calculations were based on Terzi-Hakonte method, known in ArcFault as method 1, since the customer preferred IC-based methods for this study. Furthermore, the utility operator used other IC-based programs for short-circuit studies, which are more adept with IC standards. Protected devices and their settings were more adept to IC standards as well. Third, the simulation models for study cases were used to network equivalents defined for a standard topology given by the utility. High voltage or flash fault types. Although three-phase fault is higher magnitude and is unlikely to occur in HPR flash substations and our transmission lines, we analyze single-phase, line-to-line, and three-phase faults half cycle, mainly to show our customer a comparison among the different R-flash types and the versatility of the ArcFault module. These fault conditions also exist within these substations are perhaps more likely to occur, yet our customer preferred the worst-case three-phase faults. Let's take a look at the real HP R-flash phenomena showing the alignment could be exposed to during an energized HP maneuver or during a telecontrol operation, arcing induced by weather conditions, among others. R-flash scenarios. As I mentioned earlier, in each substations were analyzed three types of short-circuit faults according with the specific topological conditions gave by the utility. Single-phase ground, three-phase fault, and line-to-line fault. The steps of the analysis are as follows. Step 1, data collection. Step 2, determine operating modes. This is how the substations are functioning with their topological conditions. And step 3, modeling in electrical power system analysis softwares. We use ETAP. Step 4, selection of the working distances according to the NESC. Step 5, run simulation of one-phase, two-phase, three-phase faults. Step 6, simulation run on HPR flash voltage. Step 7, selection of proper PPE according to standards. And step 8, final report. Now we're going to run the actual simulation using ETAP ArcFault module. We first want to show you the sequence of operation in one of the bars of 30.5 kilovolts in substation. As we may see, the sequence of operations shows us the fault clearance time on the ArcFault current, the magnitude, and if we want to see clearly what was the device tripped, opening this sequence of operation events, this shows us that is the relay 31, and the function activated the run fault temporize.
Next, we will examine some additional fault locations for the same system using the ArcFault module.
We may see now how the categories, hard flash risk categories are defined in the four bus bar surrounding the two uh, power transformers and the ring of the 34.5 kilovolt ring. Well, at last, I want to show you an important feature of the RFault module. This is the RFlash analyzer. We use the RFlash analyzer in order to group all the results for the various scenarios analyzed in our study. Then we can show their main information, main electrical parameters, and also it serves as a comparison for the worst case incident energy, and we can filter reports by energy levels with their color distinction in order to hover over the results efficiently. At last, we export the results in an Excel spreadsheet, and that serves us to set comparisons between all the substations with the next tool I want to show you. The RFlash result analyzer function was a key factor to be able to analyze the data with the Excel export feature. So I want to show you these turnout tools you can use to analyze data such as this one using the information exported by the result feature. With the Excel export information, we can see an example of what kind of data analysis we could perform, showing, for example, HRC by voltage level, HRC by substation, and relation between incident energy, volt, and equipment type, and many more. Recommendations and conclusions. The R-flash analysis determined that when considering line-to-ground and line-to-line faults, a hazard risk category 2, defined as 8 calorie per centimeter squared, was not exceeded. In contrast, if the analysis were realized using roughly method, the results were approximately 80 calories per centimeter squared. The three-phase faults results exceeded the maximum HRC as expected. However, it is important to note that this fault type is less common for T and D utilities. The G's substations analyzed were telecontrolled and if necessary with specialized personnel, but some contingencies may require operation of Bayard assets by operators that will need to use the proper PPE determined with the RFlash analysis results from ArcFault. For some line and transformation Bayards, full energization is recommended prior to work with direct voltage or maintenance duties that exceed hazard risk category over 40 calories per centimeter squared. Following with the recommendations and conclusions, at the 115 kilovolt substations, these are to station 2 and 4 in our study, the FCT was set at 250 milliseconds according to the adjustment of distance relays in their zone 2 that trips base circuit. Using RFALF module saves us a great number of man-hours when performing the study. Features a sequence of operation for our flash result analyzer and exporting data to Excel help us in a great manner in order to complete the activities necessary to give our customer solution to their necessity, complying with all the standards related. Thank you very much for your attention. Now we may pass to the questions section of this presentation.